We'll be talking today about alkenes. This is grade 11, term 3, first theme. The assessment criteria for this set of themes is to recognize the possibilities of geometric isomerism. We'll look at two kinds, cis and trans isomerism, also known as easy isomerism. And we'll put it in the context of other kinds of isomerisms that we have seen. We'll look at the mechanism of electrophilic addition, know some examples, and be able to apply the mechanism to new cases. And we'll also be able to predict the products of addition to unsymmetrical alkenes. You can see in the picture a picture of dichloroethene. There are two isomers of 1,2-dichloroethene. You can see one where the chlorines are across from each other, and you can see one where the chlorines are adjacent to each other. They are isomers. They have the same numbers of chlorines, hydrogens, and carbons, but their position is different. If the isomer has in this case, the chlorines on the same side, it's called a cis isomer. If they're across from one another, on opposite sides, they're a trans isomer. They stay in these positions because of the carbon-carbon double bond that restricts movement of the carbon atoms. The following video details the difference in naming between cis-trans and EZ.
If I were to come over to your place and say, name this molecule, the first thing you would do is you would say, well, look, we have a double bond. So we're dealing with an alkene. We have 4 carbons in the longest chain. There's actually one chain here. So it's 1, 2, 3, 4 carbons. So the prefix will be but. And regardless of which end you count from, the double bond starts at the number 2 carbon. So this is butene. Butene. I'd say, well, that's very good, and that is correct based on everything we've learned. But what about this molecule? What about the molecule that looks like this? The molecule that looks like this. And you'd go through the same process. You'd say it has a double bond. It's an alkene. Our longest chain has 4 carbons, 1, 2, 3, 4. Regardless of which end you start counting from, the double bond starts at the number 2 carbon, 1, 2, 3, 4. So once again, you'd say, hey, Sal, that's also butene. And then I'd point out that these are each fundamentally different molecules. And the reason why they're fundamentally different molecules is because this double bond can't rotate. It's got that pi bond there for that second bond that keeps this carbon-carbon bond rigid. So it's not like the molecule can switch configurations between this or it's not like it can switch conformations between this and that. It cannot rotate around this double bond. So these are different molecules. These are different molecules. Different molecules that will behave different chemically. And because they behave different, we have to have different names for them. Now, there's 2 different naming conventions. One is kind of, I guess, the simpler naming convention. And it works when we have one functional group on each of the carbons in the double bond. And then in the next few videos, we'll talk about the slightly more advanced naming scheme that will work when we have more than one functional group. So the first way to name it is if you have your functional group. So let me circle the functional group. So on this top one, our functional groups are on opposite sides. They're apart. They're on opposite sides of the carbon-carbon double bond. This is on the top. This is on the bottom. In this molecule right here, our functional groups are on the same side. So when our functional groups are on different sides, we could call it trans. We could call it trans, literally for, I believe, Latin for apart or Latin for opposite. I'm not a Latin scholar, so forgive me. But the functional groups are apart, so we call it transbutene. The other convention to use comes from the German for apart, and there we call it Entgegen. And instead of writing out Entgegen, we write E in parentheses. So we would call them, just in a different color since this molecule down here is blue. So we would call this E, E-butene. These mean the same thing, E-butene. But this is now kind of the standard convention. We'll see this notation where you use Entgegen or E is actually more powerful. It can extend to when we have more than one functional group on each carbon. So let me just make it clear that the E stands for Entgegen. Entgegen, which is German for apart. Or at least I believe it is. I can't speak German, so I'll just have to take people's words for it. Now, in this situation where our functional groups are on the same side, you could call this cis-butene. Cis, I believe, comes from the Latin for together. Or you could call it Z. Or you could call it Z-butene. Butene, and you could imagine this Z comes from the German for together, and it stands for zusammen. Zusammen. Zusammen, which is German for together.
We'll now take a look at the mechanism of electrophilic addition. Electrophilic addition is a reaction between an electrophile and a nucleophile and a carbon-carbon double or triple bond. You can see in the picture the combination of nucleophiles, OH plus and Bro minus, and their attempt to attack the carbon-carbon double bond, the pi bond. They do that because that is the weakest of bonds. Once that bond is broken, we have the addition across the double bond. Let's look a little bit closer at this mechanism. As we have a electrophile and nucleophile come toward the double bond, the electrons in the pi bond are attracted toward the positive end of the electrophile nucleophile combination. The negative side of the molecule is repelled. As the process continues, the electrons in the pi bond move even further towards the positive end of the electrophile neutrophile until a covalent bond is made. What we're left now with is a carbon-carbon single bond. And one of the two carbons is positively charged. Why does that carbon atom have a positive charge? The pi bond was originally made using an electron from each carbon atom. But both of those electrons were used to make a bond with the positive end of that electrophile nucleophile combination. So that leaves the right-handed carbon atom in a positive manner. It's called a carbocation. Because it has a positive charge, the negative end of the electrophile neutrophile is attracted to that end of the molecule. And there becomes a dative bond between the Y, the negative end of the electrophile neutrophile combination, and the positive carbocation. This was what happened with a symmetric alkene. an alkene that could be split down the center and have the same number of atoms of whatever compounds to the left or to the right or to the top or to the bottom. What happens in unsymmetrical alkenes? You see in the picture an example of an unsymmetrical alkene. You can see that there is a double bond in this alkene, but it's near the right end of the molecule, and there are other carbons that are to the left side of that double bond. Considerably more carbons to the left and to the right. So it's an unsymmetrical alkene. What happens when we provide an electrophile neutrophile combination like H-chlor, H-bro, or something like this? We have the opportunity to create two kinds of products. The major product is formed where the chlorine is added to the most substituted carbon. The minor product is where the chlorine is added to the least substituted carbon. This process is called hyperconjugation. The following video will describe to you the process of hyperconjugation.
Philic addition to alkenes. You may have noticed with our previous alkene, it didn't matter which side the hydrogen added to, because it was the same. But what if we had an alkene that was different on one side of the bond compared with the other? What's observed to happen is that the hydrogen adds to the side of the bond that already has more hydrogens. Just for emphasis, the new H is highlighted in green. Okay, but why? I'll show you in a second, but one thing you should know is that Markovnikov's rule states that for hydrogen halide addition to alkenes, the H always goes on the side that has more H's. And I was really curious, so I wrote why again. The answer has to do with something called hyperconjugation. Let's look at the actual structure and shape of this carbocation. Something to keep in mind, sigma bonds are shaped generally like this, where the H nucleus is actually outside of the sigma orbital. And you know a p orbital looks something like this. Now I'm actually going to draw one of these sigma orbitals into the methyl group next to the empty p orbital. Now when you have two orbitals like this next to each other with similar wave functions, and one of them has electrons and one doesn't, the one with electrons will donate its electrons into the one that doesn't, at least sometimes, a little bit. This slight donation of electrons stabilizes the positive charge. So with all of that in mind, let's look again. Back to our asymmetrical alkene. We're going to look at what if the H added to one side, and then what if the H added to the other side. In the first case, the carbocation would look something like this. I'm going to draw one sigma bond on the methyl group, but keep in mind there are 3 identical ones like that. Each one of them, when they're properly aligned as the methyl group rotates, provides some electron donation. Now, if the hydrogen had added to the other side, our carbocation would look something like this. Now there are 2 methyl groups donating electrons. In this case, the number of stabilizing sigma bonds directly next to the empty p orbital is 6. On the other side, in the other case, it's only 3. That hydrogen does not count. Its sigma bond is orthogonal to the empty p orbital. So, the species that is more stabilized has a lower transition state energy, meaning that's the one that happens. So to summarize, Markovnikov's rule says H's add to where there are more H's, because of hyperconjugation. Thanks for watching.
Here are some questions to start your thinking. The first question, cis-trans isomerism. The second question talks about mechanisms. Why is a carbocation necessary? And Markovnikov's rule. That was the one with unsymmetrical alkenes. What happens if we have 2 double bonds and it's an unsymmetrical alkene? Does the rule still apply?